So the motivation of our study, we're studying coronary heart disease as it is one of the leading causes of illness worldwide, and identifying the risk factors associated with its development is crucial for preventing and treating this disease. By studying certain chosen risk factors, we hope to gain a better understanding of the factors that contribute to the development of the disease and identify strategies for preventing it. By fitting a logistic regression model, we can estimate the effects of multiple predictor variables on the likelihood of developing the disease over a 10-year period. This enables us to identify which risk factors are most strongly associated with the disease and make predictions about a person's individual risk profile. Additionally, we can control for potential confounding variables, which will help us in producing more accurate estimates of our predictor variables. Overall, by fitting a logistic regression model for this dataset, valuable insights into the risk factors of coronary heart disease are provided to help aid in preventing it and treating it. Choosing our data set, we obtained our data from Kaggle.com. The information from this data set comes from the World Health Organization, and it has information on over 4,000 patients with 15 attributes. For our binary response variable, we chose 10-year CHD, that being coronary heart disease over a 10-year period. For our number of predictor variables, we had 4, and they are all numeric in nature, those being age, cigarettes per day, and body mass index, and systolic BP. The number of observations in our data set for each predictor had over 1,000 observations. And our overall research question was, what is the relationship between smoking behavior, body mass index, systolic blood pressure, and age, and the likelihood of developing coronary heart disease over a 10-year period? So as mentioned, we obtained this data set from Kaggle, and it was of high quality, so we didn't need to manipulate the data in any way. We used proc import to get the data into the SAS data set, which allowed us to easily work with it. When producing our panel display of scatter plots for each predictor variable versus the binary response, we found some interesting characteristics. 6 per day appeared to have a nonlinear relationship with 10-year CHD, with some variability when it actually went down at 40 plus. This suggests that smoking may have a complex relationship with the risk of developing coronary heart disease. Age, BMI, and CIS-BP all seem to have a linear relationship with the response, but CIS-BP appeared to be the best fit. This is supported by the results of our logistic regression model, which found that higher levels of systolic blood pressure were significantly associated with an increased probability of developing coronary heart disease. This will be discussed at length further in our presentation.
The logistic regression analysis shows that higher systolic blood pressure is significantly associated with an increased risk of developing coronary heart disease. The parameter estimates table shows the estimated log odds of developing coronary heart disease when CIS-BP is equal to 0 is negative 4.99. And for each 1 unit increase in CIS-BP, the estimated log odds of the outcome increases by 0.024. These estimates and their associated standard errors can be used to calculate confidence intervals for the estimates and test hypotheses about their values. We found that systolic blood pressure is a significant predictor of the probability of developing coronary heart disease. The chi-squared statistic for the likelihood ratio test is 178.9, which shows that the model with its CIS-BP provides a much better fit to the data compared to the null model. This means that our model with CIS-BP is statistically significant, providing a better fit to the data than the null model. There's only 1 degree of freedom, indicating that there is only 1 parameter difference between the models. The p-value is less than 0.0001, which means there's strong evidence against the null hypothesis. The empirical logit plot produced from our dataset shows linear relationship between the observed proportion of outcomes and the predicted probabilities. In terms of its consistency, the points on the plot appear to be evenly distributed around the diagonal line. This shows that the predicted probabilities are consistent with the observed proportions of outcomes. In terms of deviance, the plot does not show a systematic pattern of deviation from the diagonal line, indicating that the model does fit well. In this step, we use proc-reg to investigate any potential multicollinearity, which is when the predictor variables are highly correlated. The main problem with this is it can increase the standard error and throw off regression estimates. Analyzing the output, we can see that they all have a variance inflation of about 1, and this is good because low VIF values indicate low multicollinearity, or that our variables are not too closely related. Based on our logistic regression analysis, we used a variable selection method to fit the best model. We used a backward selection process to determine significant covariates. Body mass index was removed in the first step and the process ended. The model convergence status indicates that the model is a good fit for the data, and the model fit statistics suggests that the model with covariates is a better fit than the intercept-only model. The results of the residual chi-squared test suggest that the model fits the data well, as the p-value is not significant. This means that there is no significant lack of fit in the model. The intercept estimate of negative 7.75 estimates log odds of developing coronary heart disease when all covariates are 0. The standard error of the intercept estimate is 0.365, which represents the degree of variability in the estimate. The Wald chi-square statistic is 451.6, and the associated p-value is less than 0.0001, indicating strong evidence against the null hypothesis that there is no relationship between the intercept and probability of developing coronary heart disease. The point estimates of 0.069, 0.028, and 1.017 indicate the increase in the odds of developing coronary heart disease for a 1-unit increase in each of the covariates.
So when looking for a probability of success for the response, the hidden white trick is used by inputting self-constructed numbers for each of the variables. The hidden white trick creates a fake observation, which in turn can be used to predict the probability of a response based on inputs for the different predictors. In this case, for age, we use 45 for 6 per day 24 and cis-BP 120. By creating the dataset, an observation is made to combine the real dataset with the hidden white trick dataset. A new dataset is created to combine and concatenate the two datasets into one. Once both datasets are combined, a proc logistic is used on the dataset to find the predicted probability of success. Once a probability of success is created through proc logistic, a proc print is used to print out the probability of success based on the inputted variables. After using the proc print step, a table is generated in which the user-generated observation is placed at the top. While there is no response variable for the user-generated observation, the predictor variables each have variables inputted that are used to predict the probability. Looking at the p-hat, the probability based on the inputted response variable comes out as an 11.5% chance of success. This means that if a certain person had these specific response variables based on the model, the observed value would have an 11.5% chance of success, or in this case, the 10-year CHD. When looking at the ROC curve for our best model, which includes age, 6 per day, and cis-BP, we can see that the area under the curve is 0.7186. With the number being greater than 0.5, the model is better at predicting an outcome compared to random chance. With 0.7186 not being the highest, it indicates that the model is good but not amazing. The ROC curve shows how well the observations can be discriminated and predicted correctly. With the curve of 0.7186, there's about a 71.86% probability of discriminating and predicting the response variable correctly. When looking at the second ROC curve, we can see that it only has 0.6564. This curve only utilizes one variable, cis-BP. While the model is better than a random chance, the area under the curve is lower, meaning the model is not the greatest at discriminating and predicting correctly. With a curve of 0.65, there's about a 65.64% probability. Since the area under the curve is less, we lean towards using the model with 3 variables versus 1 variable. Overall, our analysis using logistic regression provided insights into the risk factors associated with developing coronary heart disease. Our panel display of scatter plots revealed that the smoking may have caused a complex relationship with the risk of developing CHD, while age, body, BMI, and systolic blood pressure all had linear relationships with the response. The final model included age, 6 per day, and cis-BP, and was found to be a good fit for the data. The ROC curve indicates our probability has a 71.86% probability of discriminating and predicting the response variable correctly.